Ladies and gentlemen, thank you for coming for this presentation. Covered another super tall building in China, Wuhan Greenland Main Tower. So it's about 600 meters, 6 and plus tall. And when we design a high-rise building, and we team up with AIGG for this high-rise building, and also we design a Kingdom Tower more than 1 kilometer tall. So although this Wuhan Greenland Center project is not as tall as the tallest building in the world under design, but it really has a lot of unique feature that I like to cover today. And also I will emphasize how great architect can help structural engineer to achieve structural efficiency, how structural engineer can achieve the structural efficiency without hurting the architecture beauty, and how the structural engineer can simplify the curtain wall system to avoid the high construction cost. So first, let's start with the general information about the Greenland Wuhan Main Tower. So it's 606 plus meter tall, and when they finish, will be ranked the number 7th tallest building in the world. So, and also we have some general information about this gross GFA, so about 339,000, and with 323,000 above the ground, and also with a 5-story basement. It's a mixed-use tower, features an office building, apartment building, and also a high-end hotel at the top. On the top of the building, you will see a special crown and dome structure. So the owner is the Greenland Center Binjiang property, and the design team, we have ASGG as the design architect, structural engineer is Soren Tomasetti, and positive energy practice as a mechanical engineer. And we have our S team, LDI ICATI, as the local design institute for this project and serve as the engineer of record. So this paper was contributed by myself and also a colleague from Dennis Pong and Mike Standertil, and also we have Wang Banteker and from ASGG. A special acknowledgement to the RWDI, who is the wind engineering consultant for this project. So all the high-rise building, and when they become tall, the lateral on this tower becomes significant and play a big role, important role, maybe the most important role in the design of the structure system. So let's see, engineer always ask the question is, which one is governed, so wind or seismic? So from this chart, you can clearly see that under 100 wind, when you compare 100-year wind to the frequent earthquake, you will see that in terms of shear, the wind load is 45% larger than the seismic, but when they're talking about the overturning moment, so this difference increased to 80%. So, and we face a challenge. How can we reduce the wind load? So this time, I want to have not only we can solve this from structure, but we can solve it from some special architecture features. So let's welcome Wang Banteker from ASGG to show us how to reduce the wind load from the special architecture way.
Thanks, Paul. Thank you, Paul. Yeah. So thank you all. So working with our colleagues at TT, we understood that the wind was really controlling the issues in this building. And our firm at ASGG, one thing we look at is these buildings as performance machines, very similar to what Mr. Wilkins spoke about earlier. We look at it like a car, like an airplane, like a machine that works, that functions to perform. So we looked at how can we deal with these wind issues, and how can we optimize the shape to be able to do these things. So there's 4 basic principles that we looked at. The first one, which we now understand, is the tapering of the building. By tapering that form, we know we're going to reduce the wind loads as the building gets higher, as we go up in space, and we smooth that shape out. So we take the program, which begins to reduce in lead spans as we go up into the space and create a smooth body out of that. The second thing is that we looked at rounding the top. We know the winds are stronger at the top. How we deal with the top of the building is a very important component of how the building performs in general. So we created this round top, what we call doming the top of the building. We learned that from previous jobs that we worked on, other projects that we've done, high-rise buildings. understanding how that really helps the shape of the building. And the third component, it's really kind of what we call the triangular floor plate, which we talked about in other projects before, and just softening the corners of the building, understanding that wind shedding, that vortex shedding as it goes around the corners, and how that really helps get the wind to go around the building and maximize the performance of the building. So all three of these are pretty common. We've seen in a lot of buildings. And then the fourth one is the one that we kind of introduced. We sing as well in Shanghai Financial Center, the top opening. But what we wanted to do is kind of bring that further into the building and find out how can we introduce more openings, work with the building or the shape of the building to kind of get the architecture, the structure, and the mechanical systems to all kind of work together and help optimize the systems. So what we did at that point is that we took, at the beginning of the project, we took some basic models into the wind tunnel. So the first one over here, as you see, is the basic tapering shape, but it has no openings. It's a solid shape. So that's kind of our control subject. We know how that's going to perform without creating any openings into the building. And then we looked at two kind of different schemes of how do we introduce openings into the body of the building to kind of help with that wind issues. Option two is kind of what we ended up with, where we have large openings in the building. So we have the large dome opening at the top, and we have secondary openings throughout the body of the building, and that kind of really helps kind of reduce the wind shedding. And then the third one, we looked at it, well, that's kind of 4 large openings. What happens if we introduce the concept of having a lot more smaller openings throughout the entire body, see what that performs. And then we can look, I think you have this, yeah, you have the results. So we looked at both of those, all 3 of those options with a control option to understand what the difference. It was clear coming out of the wind tunnel when we went back and forth with TT that option 2 performed the best. The larger openings throughout the body of the building were the ones that are doing the most work. Paul, you want to talk about this slide?
So you can see that from this chart, clearly identify the second one can reduce the wind load by 15% in one direction, 7% in the other direction.
So here's the same diagram talking about vortex shedding, how the whole building begins to now begin to deal with that corner, the rounding of the corners, the doming of the top, and all those 4 components architecturally coming together with the structure of the building to perform as one unit. It's one integrated system. And that is actually, actually, I think it's in the previous slide. You can talk about the framing?
So, after this, I will quickly go over the tower lateral system. So this project tried to emphasize the structure efficiency. So for all the high-rise building, we always have some special structure element you can take advantage to form your structure systems. First thing, let's see, the one in the red in the center of the building is the core. So the core, you will see that is in Y shape. So compared to equivalent area of a rectangular shape of core, this Y shape is to offer better stiffness. So for super tall building, when they grow in very tall, the stiffness is become a biggest challenge to the structural engineer. The second element we try to use to enhance this structure efficiency is the super column. So this, you can see that this plane is in the triangle shape and have 3 corners. So to get those structure stiffness, so all the structural engineers know that the structure stiffness is proportional to the AD square. It means you have to take advantage the plane dimension. So try to locate it structure element with large area located at the outermost edge or corner away from the center of the building. So that's why you see that we put a 3-set super column at the 3 corners of the building. So we call that S1. So that's total is 6 super column. And also you will see that between this 2 super column, there's we added another 6 super column to cut down the span. And also we have at the end, at the parameter, we put a belt truss to form a so-called moment frame system, microframe system. And in China, they have a special requirement for the stiffness of the parameter frame. So we have added brace frames at each set of the structure, the super column. So due to the time thing, we just want to show the video to give you you can get a better idea about the structure system. And from this one is showing the elevation to show you all the outrigger system, and as a evenly distribute along the building height, and the right side is showing the outrigger, showing the bell truss. It kind of take advantage of all the refugee level, so it's close to evenly distribute to form a mega frame composed of super column and this bell truss. So this is a movie we created, so it's a silence movie. So Wong, can you help? We can sing something? So it's a structure movie to highlight all the structure systems. So you can see that super column at the corner, and this is top special crown structure, and at the you will see in the middle, you can see all the bell truss, and also you can see that between the super column we have so-called EBF and the eccentric brace frame. This some flies through at the mechanical level where we have this bell truss. So at the mechanical level, we need the stiffness. We take advantage the mechanical height, so we can offer about 10 to 12.5 meter deep bell truss, and also outrigger. Yeah, almost finished. Yeah, this is a wheel from outside. Yeah, that's okay. So for this, yeah.
So as we continue to develop the scheme, we really got into working on what we call the wind slots, which are those openings in the body of the building. And they really kind of signify that working together between us, TT, and PEP, which is our mechanical engineers. When we started the design for the building, we wanted these wind slots to be located at the mechanical floors. We wanted them to be the intakes and the exhausts for the mechanical floors, so we don't have louvers across the face of the building. So we incorporated both the architecture and that. The first issue we came up with working with TT is that, well, we have belt trusses and outriggers in these floors, so that's not really going to work. So what we did is that we actually took those openings and we slid them to the floors below the mechanical floors. So we took the ceiling of the wind slide is now used as the exhaust and the intake. We still get the wind passing through, which helps with the structural conditions. And then we managed to program the spaces. So now they're not just mechanical spaces or structure spaces, they're architectural spaces. There's a hotel on the top of the building who loves these spaces for their outdoor spaces. The bottom of the office component we're using as a plaza as an outdoor space. The mid-span one we're using that for window washing equipment. So we're trying to find ways to architecturally use these spaces. So they're not only mechanical, they're not only structural, but they work all three components of the building. So it's completely integrating to our design.
So through the coordination, we can create a harmony between the structure and the architecture. We achieve, using the traditional truss system, we achieve efficient and cost-effective structure. But that created another problem. So as due to the opening at the floor, the corner, so we have some problem with the progressive collapse analysis. And you will see that this one identified that if you have some column is gone due to some extra events, so the loading can go up through the steel column, be hung from the bell truss above. So this is create an alternate path for this progressive collapse of this parameter frame. But if there's an opening and just immediately after, below this bell truss, that is highlighted into in yellow, so the path is gone. But we can do is structurally, we just design this beam can be span between the super column and the column adjacent to the column that can be destroyed. That way you see that cross and identify the bottom. So at the top of the structure, we have a special a dome and a crown. And for architecturally, it's about 35 meter tall. And we architect want to achieve the sculpture on the top. So we went over maybe more than 10 schemes. So eventually we choose a very simple scheme. So we call the tripod. So you will see that from this tripod, it has 3 legs and rising from the corner of the super column and sitting directly on the top column and connected to the embedded steel. So have a very sound support at the end. And also this 3 trusses, all composed of steel trusses, can rising to the building top and form the whole skeleton. And also we have some curved girds to span between this the tripod leg and also hung through the rod to the top of the crown. So create a very column-free area at the dome and create the best view for the architecture. So this is rendering from inside to see the dome. And also at the top, we have another structure system. An architectural feature is called a crown. So this is about 61 meter tall. So same thing, we are create a tripod shape. And but this tripod shape, the trusses is if you cut, and the plane is a trapezoid shape, so can hide all the window washing machine for this dome. So performance design is a requirement for all the high-rise building in China. So when we do this, we have to run a nonlinear analysis. So this is the original scheme. You will see that there's a big offset. This is a 91 story. It's a big offset of the shear wall from the column here to set back dramatically inside. So this creates a big problem of witness overstress in the shear wall, and also the computer time for one seismic curve, and we need to run 1 week. It's just too long due to the nonlinear behavior. So with this time, we talk with architect. We work together and we'll bring the wall from the 91 to 23 story. And after that, we saw reducing the core damage and cutting the analysis time to about 2 days. And also by doing this, reduce the type of the room for the guest room and for the hotel is surprisingly welcomed by this hotel operator. For this kind of building, and there's a very special curtain wall system, and become very complex. So we'll ask help from our in-house structure engineer to solve how to simplify the curtain wall. So we'll ask help from Mark Dendersill. He will present how to simplify this curtain wall system.
Thanks, Paul. So everyone here knows Dennis Poon. So everyone here knows that Thornton Tomasetti is a structural engineering firm. But what you may not know is we also have a building skin practice where we act as a facade consultant for the project. So in this case, it was very convenient for Wuhan to give us a call because, as you saw earlier, when they were doing the wind tunnel tests, the building developed as a tapered form. And the tapered form develops warped surfaces, which are no longer flat or planar. And the only way to do planar glass with that would be to do triangles, and most of us don't want to do triangular glass. So the problem of warped glass or warped curtain wall panels is that there's edge seals which tend to suffer damage when they are permanently warped into some position from a flat position. So initially when Juan called us, he asked us to use some parametric software such as Grasshopper to review the form of the skin of the building and basically do an evaluation to show which parts of the building could be done with flat glass and actually force it to be warped versus which areas may be too excessive of a warp and may be problematic. So this is one of those studies where the red areas were deemed to be excessive, just as an example. So we had to do a few activities. Commonly, one of the things that we need to do is we need to clean the geometry of the skin. And at the right, you can see that this is the revised plan at any particular level, where we actually revised all of the curves from the plan to actually be a single radius. So they're actually parts of a circle, which have been combined to reconstitute the original plan. But we also did that in section. So over the height of the entire building, each X marks a point of a new arc. So it's a new portion of a circle. So all of these curves are perfectly tangential to each other, but we basically redefine the entire tower from circles rather than from the B-splines that are common with Rhino. And as we took the analysis forward, though, even with the clean geometries, from a constructability standpoint, we found that the warpage was still very excessive at the upper portions of the tower. So ultimately, we recommended rebuilding the skin by stepping back at each floor. So there's a slight step back and there's a misalignment from one floor to the next. And we developed everything with conical forms. So actually each floor, the glazing leans back towards the core, but then at each floor level it steps back in varying amounts, which allows for the differential warpage to occur. And then basically we use Grasshopper to reiterate and rebuild the entire form. And over on the right, you can see that each floor is kind of stepping back ever so slightly, but those step backs are, they vary along the entire perimeter of the floor. Thank you.
All right, so for this presentation, we emphasize that seamless coordination between the architect and the structure, and also facade engineer, we can optimize architecture and the structure and also other discipline. And second, the special architectural feature can help the structural engineer to achieve the structural efficiency. And the last one, the structure optimization, and can add the special character to this architectural feature as well. So, thank you.